Hi. So the name of this topic is testing facial recognition system security. So what I'm gonna tell you is like how we can actually test various AI solutions, and the facial recognition system is just one example. So you can apply those methods to other solutions as you want. My name is Alex, and I spent like 15 years in cybersecurity, and I'm not a big expert in AI. However, my first AI application was intrusion detection system, which I wrote when I was a student. So I pretty much understand like AI and cyber. I'm a founder of Adverso AI. It's a AI security company based in Israel. I'm also author of two different books in cybersecurity, one about the databases and another one about the applications. And also a big fan of basically hacking everything from like biohacking to synthetic biology, like genetically modifying cells and bacteria, and also a big fan of neuroscience and so on. So I'm really excited of hacking various things, and AI is just one of them. And so our mission in Adversa is to increase trust in AI systems by protecting from attacks and enhancing its security, privacy, and so on. And how I came to this, to the importance of trust is basically I spent a year in traveling all around the world, and from various places, from like deserts of Oman to Amazon, and I was asking absolutely different people, would they, various questions about the future, and one of the questions was, would they sit in the self-driving car? And most of people said, no, like absolutely, we don't trust it. And then I realized that it may sound funny, that they don't trust it, but I mean, those are our potential clients. And if people don't trust the new technologies, it's the most important factor that we should solve. Because if we won't solve it, if we won't solve the problem of trust in AI, we may experience the new AI winter. So this is very important, and that's why we decided to put all our attention in increasing trust in AI. And it's a very big topic, so we mostly focus on the security part of AI trustworthiness. Okay, let's get back to the ground. And this topic, this presentation will be a little bit about AI security, and then how we can basically assess the security of facial recognition system. And you can apply this approach to other solutions. Okay, one more important thing. So if we take a traditional software, right, and we interact with this software using the graphical interface, basically we have some inputs and we put some information, some structured data into those inputs. And most of the vulnerabilities in the software industry is actually putting some kind of unstructured data, like SQL injection. So the system waiting for some data, but we inject some unstructured data that the system don't want to see. And if we take the AI solutions, the all interaction between the systems will be like visual, audio, and some kind of like non-structured data. And the thing is, inside this unstructured data, we also have the new types of attacks like evasion, poisoning, data exfiltration. And this is a big difference. So we don't even know how to basically solve the problem of vulnerabilities and injections in structured data. But now in AI, and actually in machine learning algorithms, we have problems of filtering unstructured data. And this is a new threat. And this is something where we need to focus a lot of attention, because it's a completely new area with the new types of attacks, new types of security solutions, and so on. And this now is just the beginning of this area, actually. So, and even now, we all already saw a number of examples affecting confidentiality, integrity, and availability of machine learning-based solutions. So, for example, the malware detection engine, AI-driven malware detection engine from Silence was hacked and bypassed because of the vulnerability in the machine learning algorithm. And there are various examples of such attacks. And also the number of research papers in this space is really growing. Like by the beginning of this year, we had 2,000 research papers. I think currently we don't have a final calculations, but it's more than 3,000 research papers currently in this topic. So this is really huge area. And we can find examples of AI in every industry. And basically why we choose the facial recognition, one of the facts that we choose it for testing is because facial recognition is basically almost everywhere. You can see it on the slide. Then, so what kind of attacks actually I'm talking about, right? So first one is evasion, or it's also called adversarial examples. And most of the research papers actually about the evasion attacks. So basically when we fool model detection or prediction, and there will be examples in another slide. The second most popular attack is poisoning, when we retrain a model on malicious data. Then we have a model inversion, when we steal the data, the model data set actually. And then we have a backdoors, when we inject the data in the model, inject like a new behavior in the model. And also we have a model extraction, like we steal model internal parameters. So in this presentation, we will only cover the evasion attack. And I think most of you hopefully heard about that, but very simply, in this attack, what we're trying to do is we're trying to change the picture. If we talk about the computer vision, we're trying to change the picture in such a way that the changes will be imperceptible for human, but the changes will be will affect the model. And actually how we can do that, simply we need to discover the most important pixels somehow with different methods. Then we need to change those pixels, to add them, and actually the model will make a wrong prediction. And there are a lot of different ways how to do that. Okay, so now we're going back to our initial goal of testing a facial recognition system. And the first part is applying different attacks. It all started with a case study, the real story that one a smart home solution provider asked us to check. So their goal was to find the most reliable combination of hardware and software to apply to the critical facility. So our goal was to check like how different software and hardware facial recognition solutions and their combinations can be affected by adversarial attacks. And the most important thing, that it should be done in the physical environment. So it's not like just changing, the pixels in the photo, it must be a real physical attack. So what is the problem? First is that there are over 2,000 research papers in this area, and you need to understand, and you need to really understand like all of them, or maybe not all of them, but you need to at least understand how to filter them. Secondly, around 100 research papers were on the testing facial recognition systems. Then the next problem is there is a countless combination of different types of attacks, models, and environment. And basically, I think, you know, like most of the research papers, they test something on a specific environment. So you have 100 research papers, but all of them have different types of attacks, different models, different environments, and different everything. So you cannot really compare it. So, and finally, you don't have real understanding of the real world risks, because you have a lot of research papers, but nobody knows like if this attack really can be applied to physical world, and if it can be applied to physical world, is it real? Is it works with the multiple? Can it be applied to the multiple facial recognition systems and whatever? So we decided to apply the structured approach, how to test it, and finally help the customer to find the right solution. So first of all, before we start to filter all the research papers, we should answer the main question, the attacker goal. So it can be, the first question is why. So what is the, why attacker trying to attack this system? It's either confidence reduction or it's a misclassification. So just to avoid detection, or it's target misclassification when we pretend to be another person. So first of all, if you test something, you need to choose what is the goal. After you choose the goal, you need to analyze what can you do, and in here you can say that it's actually attack constraints. So one of the most popular attack constraints is different L norms. So simply, can we change every pixel, or can we change only a few pixels? Because in the digital environment, most of the adversarial attacks are performed by changing a lot of pixels a little bit. In the physical world, most of the attacks actually change a few number of pixels, but change them a lot. So the second thing, we need to understand that what are the constraints in our environment. Then it's more detailed question about constraints, like which form we can apply, because if we talk about the facial recognition system, right, we can do different things. We can create a mask. We can create special glasses. We can create a head, a mustache, a band-aid, so everything. But we need to understand, like in our particular environment, what kind of things we can do. Can we use glasses, or it's some kind of facial recognition system which asking you to took off your glasses? So if it's this system, we only can do like other modifications, like probably band-aid, or probably some kind of retina changes or something like that. So the next question is the form. Then we have attack conditions. So basically, it's various approaches to, for example, optimize the quality of patches for printing, because when you physically print something, the color of pixels may be changed. You need to adjust your attack to inconsistency of colors, because it can be different lights in the physical environment. You need to apply, adjust it to the various patch positions, sizes, angles, and so on. So a lot of different constraints. And only then the final thing is like how you perform this attack. And there are various methods like FGSM, the most simple one, fast gradient sign method, or they can be more complex, like momentum FGSM, or any other approaches that basically doing the same thing but maybe faster and more effectively. Then after we understand like how we can perform the attack, we need to have some attack success criteria, like what is a perfect attack for us? Is this attack with the best misclassification rate, or if this attack with the best imperceptibility, which is the attack which is hard to detect, right? Or if our goal is to make the most robust attack, for example, if we talk about the glasses, we want those glasses to work not in the situation when we just show those glasses like directly, but we want this attack to be super robust. We want those glasses to be to work on different directions, different sizes, different angles, and so on. And the computation. So it is possible to create some super attack, but some of the attacks may cost a lot of money, because you spend a lot of computer resources to calculate this attack, and it's also very important success criteria. And finally, so what we found, that first of all, it's possible to perform a physical attack against facial recognition system. You can see the example on the slide. Secondly, we understood that glasses and bandanas have the best misclassification rate. So this form of attack is the best one. We also understood that it's possible to further optimize it to make those glasses smaller and so on, but it was not the goal of this task. The goal was to find some universal, the most precise attack on which we will test solutions. So the second part of research was to test models and compare them against this universal super attack. And there can be different goals why we test models. We can test models against white box attacks, just to test different models, or we can test models against the black box attacks to understand how models are protected from transferability. So the transferability is the thing that in most cases, if you calculate attack against some machine learning model with some data set, this attack may be transferred to another module in another data set. And depending on various parameters, this transferability will be better or worse. And the goal of this test was to understand what are what factors affect transferability. So, for example, is it a model size, the data set size, and so on. And there are different model conditions, starting from the architecture. There are different architecture types, different data sets, and different types of outputs, if we talk about the facial recognition system. And the goal of this part was to understand how each part, how the architecture affects transferability, right? So, for example, if you apply attack on VGG, if this attack will be relevant for capsule network system, and so on. So the testing approaches are the following. So we can prepare attack on random model or on the same model. We can prepare attack on the different or the same conditions and different on the same output, and so on. And finally, we can prepare attack on the ensemble of models, which is the best approach. If you apply attack simultaneously against different models, so the more models you have, actually it's better. And so here are the results very quickly. So some of the results, because most of the results are under NDA, but just to show you like what kind of results can be achieved after this testing. In our environment, like models with more layers were more secure. Preparing attacks on random models is not effective. Attacks on the same models but different, actually not even landmarks, but outputs in general are effective. And of course, if you prepare an attack on the ensemble of models, it's more effective with each new model. The thing is, the results may be absolutely different for your machine learning solution. And here I'm just giving the approach, right, and the results that we experienced in our environment, just to give an idea how it works. Then, after we tested the models, basically the algorithms, we need to test the environment, because, okay, we can find that before testing environment, we can only say that this algorithm is more protected from attacks, but we have no idea how this algorithm will work in particular device. Maybe, like if we combine it with a different device, the algorithm will be more secure or less secure. So we need to test devices and environment. Why? Because reality, and it's much more complicated than the just research and test against some models without environment, because there are different environment features, camera features, and so on. Simply, there can be different environment, like distance to objects, lights, brightness, and so on. In some environment, attacks can be better. In some environment, attacks can be less better. Then we have device features like resolution quality or color rendering, and different colors can be rendered absolutely differently in different devices. So it may happen that you have perfect attack for one device with like good resolution, but then you apply this attack, this mask or glasses on another device, and it just don't work completely. And also there are like less important but existing things like codec compression and data transfer compression, which may also affect stability of attack and defense. So there are different approaches how you can test your physical attacks against different environment. Like you may have some fine function for big pixel difference. So for example, when you calculate the attack, you may tell your function to not make a big pixel difference because pixel difference in so there should not be two pixels together with very big difference, because in the real world the camera will not detect this difference, right? Then you need to train your attacks with various sizes and angles to be so that attack will be prepared for a physical environment. You can add or subtract color changes. For example, you may know that this camera changing the red color to pink color. So you may extract some values from the red color before making attack, and then add this value while making attack. And different Gaussian blur, black and white, and so on. There are a lot of different approaches how you can make attack in such way that it can bypass different environment. So our results are those, like cameras with better quality are more vulnerable, said true. Cameras rendering, color rendering may seriously affect attack success. Black and white attacks are more stable. Light brightness may slightly affect color patches, but in general, it's not a super big problem. So those are some of the most important results. It's very important for our goal to find the best combination of software and hardware. So because of the camera quality and attacks, and our goal in this task was to find a solution so that the camera will have good quality, and at the same time the algorithm will be not vulnerable even with the camera with good quality. So it's a quite challenging task. And finally, we should test different defenses, and there can be different defenses depending on your so who you are, because if you're enterprise and you're buying those devices, like in our example, there was a solution provider who is buying devices. They cannot change something in those devices. The only way for them is just to choose the right combination of software and hardware. Or they can be a company who provide APIs like cloud platform. So they may have more options. They may apply some defenses on top of algorithm. Or you may be a hardware vendor and you're buying the software from someone, and this software may be vulnerable, and you cannot do something with that, but you can also apply some additional filters and so on. Or if you're a software vendor, if you develop your own machine learning solution, you can apply other approaches to defend your solution. So it's the defense really differs by the type of the company. So those are the most common categories of defenses. First is modify training phase. Basically, it's adversarial training. So you create adversarial examples and then you train your system with adversarial examples and hope that it will work. But in general, it's not. You can modify model, add new layers, change it to specific activation functions. There are multiple research papers on how you can modify model. You can modify input, JPEG compression, the very simple and obvious approach, but there are at least like dozens of papers with different types of model input changes. Or you can apply different detection approaches, supervised detection or unsupervised detection. So finally, what we understood after applying different defenses. First of all, like there are no one-size-fits-all protection. This is a big problem, and I think it won't be some universal solution for each model and each data set and each algorithm. So you always need to test various defense approaches which will work for your solution. Why there are no one-size-fits-all solutions? Because various protection methods have their own issues. Like modifying model may be really a good solution, but in most cases it decreases accuracy. So your solution may be like super protected, but the accuracy can drop like significantly. Modified training, like adversarial training and other examples, is very expensive because you need to retrain system, and in mostly adversarial training, it's not like just retraining the system. It's basically, it can be like 10 times more complex than just training, because you need to add a lot of examples, and so adversarial training is really expensive, and in most cases it can be easily bypassed again just by applying new attack. Modifying input, it's also a good approach, but it's complicated, and it's very task specific. So you may create your it may work for particular model, but once you will change your model to do a little bit, all your defenses should be changed as well. Detection is also, in most cases, it's the best method, but unfortunately, this method applied when attack already executed. So you only can detect it afterwards. So the takeaways, the best approach is to have the secure AI lifecycle. If we have in the software development, we have SDLC. So in AI, we also need to have some kind of SDLC, and it consists of 4 stages: predict, prevent, detect, respond. So we need to conduct security tests first, then apply some basic protection measures, then apply some detection to monitor threats, and respond, so continuously react on the changing environment and retest it. So few next steps, just like train your AI and security teams on this topic, so that the teams will be aware of it and can work together, because protecting AI systems is really a very complex task, and it involves experts from AI, from security, at least from experts from those two sides. Then after you train your team, you need to conduct first AI security tests, even by yourself, just to understand and get an idea, address your first security findings, and then integrate those steps in your security lifecycle, and automate it and do it better and better. So thanks a lot for listening. I hope you enjoyed. If you want to talk about how to secure AI systems, you always can write us, email, contact us on the website. You can write me directly. What else? So yeah, I'm very interested in any feedback, and we hiring like continuously, and we'll be happy to talk with anyone who interested in protecting AI solutions and like making AI more trustworthy. We can find ways how we can partner with each other. So again, hope you enjoyed and have a good day. Thank you and bye.